It's ow! Actually, it was better before. Now I can't speak. Nico, can you switch it off? Sorry, but this is... It's so bad. Sorry, I have no idea. How you switch? No? Okay. So, yeah, so fluid construction grammar is currently implemented in Lisp. So it's a symbolic framework, essentially. What we're trying to do is to... It's better. So we're trying to change from the symbolic representation that we currently have to a more numeric and then eventually a neural representation of this particular framework. So what it would essentially allow us to do is it would give us an access to a whole heap of machine learning methods. So you could bridge the symbolic domain with the machine learning domain, which is obviously in itself quite an ambitious issue. And it's very complex. It sort of requires a different way of thinking about the whole framework as such. But we are trying to make progress towards this goal. So if you look at what we have to implement, you need to start from basic FCG entities that we have in the system. And what are they? Well, at the most basic level, it's symbols. So everything is a symbol. So basically, you can have a lex class, which is a category, or a noun, which is another, for example, a category or a number or plural, and everything is a symbol in this framework. Then we have feature value pairs, which are essentially pairs of those symbols joined together. So feature is a symbol and value is a symbol as well. And these feature value pairs can form feature sets. So the third item there. Which is basically a set of feature value pairs joined together. The next level up we have is units, and units is like a wrapper for a set of feature value pairs. And then essentially the last, like the main thing in the FCG is then feature structure, which is a set of units. So you have a set of these wrappers of feature value pairs. What's important to remember is that, of course, we have some operations, and they are the key thing here, really, to implement the framework fully. And these operations in FCG are match and merge. So where it says unify there, it's match, and then merge is over there. So essentially, you have a structure that has to match with a whole pool of other structures. And some of them will match and others won't. So that's what match is about, is which one is most compatible with it. And once a structure matches one or two structures from the pool, they merge. So they add all the information into one. So these are the essentials, so basic essentials of FCG. So we have to bear that in mind. And now the question we're asking is, okay, so can something like this be then implemented numerically? So symbolically, it's really easy. Whether this matches that, it's quite obvious if a symbol matches another symbol. But how can it be done in numerical space? So, of course, this means we have to encrypt our operations and use them somehow in a completely different way and without decomposition as well. So some people have tried a few different approaches to implement, symbolic tasks or symbol-like tasks in neural tissue as well. But typically, the main problem with neural networks is that although they're very good for categorization and pattern recognition, that's all there is currently to them. So they don't deal very well with tasks that symbolic architectures can deal with. So reasoning and this kind of logical high-level stuff is very difficult to represent, say, a binding problem in them or something like that. So they're quite limited, actually, in that respect. So although there have been studies, they haven't been really particularly successful yet. Some people have, however, tried to do something a bit more like symbolic-like in neural networks, which took into consideration the fact that you need to deal with binding problem, etc., etc. But these things, typically what happens is they are very isolated, small examples. So they would show you a few examples here and there and say, okay, this works. But it's not a unified approach to implement something more serious. And typically they don't scale at all. So yeah, not only in terms of the kind of the spectrum of examples they're using, but also if you take it actually to neurons, it becomes completely unrealistic. This could never be actually implemented in the brain because the number is just too huge, right, of neurons, and it's not really possible. So, and that's quite largely due to the fact that they tend to go from directly symbolic to neural. So they think, aha, how can a symbol be implemented in neurons, actual neurons, without having some kind of middle layer to it? You know, it's just grounding it straight into the implementation material, which is a bit of a problem they've noticed. So some examples of such studies are these blackboard architectures here, and also synchrony-based approaches and tensor product approaches. None of them actually take into consideration still biological plausibility. So although these approaches are there, they're aware of the fact that dimensions blow up and it's not really realistic. So what we're doing is this. We're taking a symbolic FCG as it is now, and we're using this middle layer called vector symbolic architecture. In our case, we're using something called holographic reduced representations. And this is just a subset of the family of vector symbolic architectures. So this middle layer will allow us to represent everything as vectors and then perform operations that we need to perform on those vectors. And only afterwards can we put it into some neural like framework. For example, one we found is Nengo, which is, I won't talk too much about it, but it's essentially an out-of-box solution that allows you to implement neural networks very quickly. So you can just drag out things and basically connect it with vectors, and then it can just do the whole thing in neurons straight away. So it's quite a hands-on but very simple approach to, so it's a final step. Okay. Now the VSA part, which is really what this presentation is about. So what is it about? You have essentially several vectors that you need to find a way of combining into one. So for example, you have feature and you have value, right? So two things. What you want to do is you want to bind them together into one, and they have to be the same dimensionality. Dimensionality should not grow, because otherwise it'll become unrealistic later on down the line. So what you need to then have is a way of, in a sense, reducing it. So two vectors into one. And these two vectors, you have to remember, when they're combined into one, it's a representation of both of them to some degree. Then, if they are later on combined with more vectors, they should also stay as one same dimension vector. So this is why the reduced term in HRR, because everything you do is always staying the same dimensions, but it can go many, many levels up. And of course, the important thing is that you have to be able to retrieve the information. So given the features, for example, you have to be able to get all the values from this vector. So in HRR, as the approach, this specific thing is done by circular convolution. So this is the way that HRR family uses to reduce two vectors into one, and then so that you can still get all the original information back from them. Okay, so there are some people that have tried this approach before already, but they're doing it for very different tasks. So for example, Gaylor and Bod, there's a study at 2003, and they did it for data-oriented parsing, but really it's just a sketchy framework they laid out. They want to use the same approach, but it hasn't really progressed yet. And then we also have Elias Smith, which is a guy in Canada, and he does exactly the same kind of VSA-based things, but very for small-scale cognitive models, very small-scale kind of motor tasks and things like that, and nothing linguistic or to do with reasoning even or anything like this. And somebody else who's done quite a bit of work on this and a PhD thesis as well was Jane Neumann. So she worked with David Wilshaw and Mark Steedman at Edinburgh on this, but it was some time ago and she doesn't work in this area anymore. So, okay, so vectors basically are the essential part of VSA, obviously, and they can be represented by randomly generated n-dimensional, so any symbol basically is a randomly generated vector, that's all. So this is the essence of this kind of, well, approach. Yeah. Bad joke. So, yeah, so basically then you can see that Lex class, that was a symbol before in previous life, now becomes just a vector of, you set the dimensionality actually. And the same is with noun, it just becomes a vector of so-and-so dimensionality randomly selected from that distribution. So now you have to think that, okay, nothing is really a symbol, everything is just a numeric set of numbers. And the key thing to remember with HRR is that it does require a high dimensionality vector to encode features correctly, but that dimension doesn't grow. So, okay, it is high, but then after all, the operations are done, it doesn't grow, which is very important, actually. Yeah, then circular convolution is an operation. This is the main thing that binds feature value pairs under this approach. And you can see that it's actually just a set of multiplications and additions. So that's how you can think of this circular convolution. So it's also quite handy because it has some nice properties down there, and it's a fairly implementable operations as well. So yeah, very handy and easy. So you can combine then these two vectors, C and X, into a T vector. So if you think of C as, for example, the feature, lexcat maybe, and then if you think of X as the value, noun perhaps, the T contains information about both feature and the value. And then, okay, how do we get it back? So if we want to get the value back from this structure T, what you have to do is you have to multiply it by the inverse. So, sorry, convolve with the inverse, actually, the correct term. So T is then convolved with the inverse of C. And the inverse of C is really just rearranging this down here. So just keeping the first element as it was and swapping all the others, so backwards. And then, so it's called involution of C. This is how you can then eventually get X, which was, if I show you the previous slide, which was the value of C. So, okay. Now just briefly to see how some of these elements can be implemented then using this approach. So for example, how do we implement a feature set that we saw on the first slide? Well, a feature set can be implemented as really just addition of two feature value pairs, or three, or however many you have. So X and Y, Z and S, all convolved and then added together. And that vector T represents now all of those feature values, the whole list. So this is an example here. So Lex class convolved with noun, number with plural, and then they just added together, and that's your feature set. So for units, it's exactly the same. But the thing is, you have to also convolve with the unit name, so it's essentially it's wrapped around this unit name kind of thing. You can do it as triples, which we found out later after I did this. So, but it's the same actually. So whether you convolve unit with X and Y, or you convolve everything together and then you convolve it separately with unit, it doesn't make any difference. So then the last level here is the feature structures. And this is done by just adding two units together. So again, here, if this is the first unit up at the top, and this is the second unit here, they can be just added together, and that would represent a feature structure. Okay, so we can get all the values back from it, we know this. But we have to say that what you get back is quite noisy usually, because convolution doesn't preserve all the information. So what will happen is you'll get a vector that's a bit like something, quite similar. So this is when similarity comes in, because all along when you're doing these things, you have to keep track of all the vectors you know. So your lexcat, your noun, everything is getting stored in the memory, which sort of makes sense. You know these things, so you just store them, right? So similarity then will tell you, when you get your noisy vector back, it'll say, this is not it, but it's most similar to something you already know. So you compare this vector that you get back to everything else you have in your memory. And then, after this comparison, the one with the highest similarity, it'll output and it'll say, okay, it's this one. And this is your answer. So what is similarity? It's actually just normalized dot product, and it's a nice way of comparing structures without decomposing them. So it's a holistic approach here. So basically, you you get the dot product, and then you normalize it, and then you get a value which is between -1 and 1, -1 being completely different, and then 1 being identical. Yeah, so this is a way that we measure similarity here. So that brings us to the error correction, which I already kind of spoke about. But this is your memory, so where you keep all the vectors you know, so anything that was ever generated, basically, you just keep track of. And we call that symbol memory. But we also have a trace memory, which is per structure, per construction, for instance. And that's anything that you've been adding along and, convolving. So these are just raw symbols that live in the system. And this is anything that took to make that particular construction. You can think of it that way. And then, yeah, so you need... often the trick to this kind of systems is to keep separate cleanup memories and to try to compare these things individually. But yeah, you can have one if you just have, say, one structure in the population. And now, okay, so of course, until now, it's just all describing the approach, etc. But this is really some results that we got from, just in the system. So we tried structures of different length. Some were 5 pairs, some were 15, some 500 pairs. And then what we wanted to find out is, can we get all the values back? So after we've convolved everything and added together, can we then get all the values of all the features that we know of back from this system? So here's just a simple example. So if you contain all these things, can we get noun, plural, feminine, etc. back out of the system? Yeah, so these are the measures that we used, which is a precision score. So true positives divided by true positives and false positives. And these are the results we got, which is, this graph shows you basically that to correctly retrieve all the values from a feature set of 5 pairs, you need approximately, so it goes down to about here, about 300 dimensions or so. And then the same goes for 50 pairs, it's a bit more. That's probably around 3,000 there. And it's something like 30,000 for a really large 500 pair structure. But you can reliably get these values back, given that dimensionality is sufficiently high, as you can see here. Okay, so next we had to see, of course, can we think of a way to implement the main operations in this approach, which is match and merge. And we used essentially the same similarity that I showed you a few slides before for matching. So do two structures, are they similar? And we could use dot product for it again. And then for merging, we used vector addition. So now we tested, okay, so if we have two structures and if they match, how is this match affected if you change the structures, if you change anything in them? So we started this set of experiments by two structures initially completely identical. And then one of them, we're gradually taking either away the pairs or adding the pairs to it to see, okay, when do they become dissimilar enough? And when will the system reflect it? Will we get the scores that we're expecting? So this is under the example here, for instance. We have structure 1, which remains always the same, so has lex, cat, and number, for instance. And structure 2 at step 1 looks identical, but at step 2 we are extending it with gender, and then at step 3, etc., etc. So adding more values. And that's what we saw here. So this point here is when they are identical, and the dot product is 1 as expected. And to the right, we're adding pairs to the right. And as you can see, the similarity score, the match score we call it, is decreasing gradually, bit by bit, as we add in more pairs to the second structure. So what that tells us is that essentially in the beginning, yes, they're similar and it's behaving as expected. But once you are changing one of the structures, the similarity between them will also drop. And in the next slide, I will explain what that kind of means for us in FCG terms. And then to the left is basically taking pairs out of the structure, which drops quicker even. But this is expected because it's less information they're sharing in the first place, if you take out. Okay, so subsets then. This is an issue from the previous slide. If you are extending one structure with more pairs and it's becoming less similar to the original thing, that's okay. But the problem is that in FCG, we often need one structure to include the other one, and that's okay, they can still match, as long as there is some overlapping information. So for example, here, if this Lex class and SEM class are in this second structure as well, we would expect this to match in FCG. However, under this approach, the similarity will be lower and lower and lower. So having one structure as a subset of another, so far we haven't found a way to do that. But it's already good to see that at least we can use actually similarity as a measure for comparing two structures. But this is an issue that we have to address very quickly. But also, there are some ways that we think we might be able to look at this, because we could learn it probably. We could learn to see if the system can spot this difference, you know, between whether one is a subset of another. And actually, we're making a bit of progress there already. Now, okay, so I'll show you a small example here, just to explain how it kind of can work for language processing. So this is a Lisp version of FCG, and it has 3 constructions. That's kind of how they look visually. If you have a small grammar, that's how they will look visually on the interface. And so one construction is, for example, a noun, like mouse. Another construction is just an article construction, and then the adjective construction called green, for instance. What we want to do is we want to see, can we parse a sentence like the green mouse, given those 3 constructions? Of course, this is obviously very trivial in normal FCG, but can we do it numerically? So first thing we do is we create a symbol memory for all the symbols that we know of. So, you know, the mouse, etc., everything gets converted into a vector. And then we create a trace memory for each construction. So basically we are adding the features together. This will be the construction, then green construction, and then the mouse construction. All the vectors added together. Then what we have to do is, okay, we have a transient structure. It's an element in FCG that's getting expanded as you're passing a sentence. And can we now match this transient structure, which contains the green mouse, with any of the constructions that we know, 3? And if it matches with any of them, the information will get merged. And then we will get the meaning, because the feature will be added and the feature of meaning will be in there as well. So the question is then, can it be once you've matched some structures, once they've been applied, so to speak, which means merged, once they've added the information, can you then get the new values back from this structure? And indeed you can. So from the trace that we convolved, we were able to get all the values correctly. So for example, if you ask what is the meaning of mouse, it will get you the meaning that you expect, for example, agent, which is what we needed. Okay, so from there, we can say that at least up until this first part, we were able to recreate it in a very, very, very simple way, of course. We were able to recreate the match and the merge operations. But afterwards, you know, like the second step, because of course it can go on for a long time, trying some more constructions based on the new information. Maybe more of them will match now. But we can't yet do that because we need to take into account the the subset issue. And when we can see whether one is the subset of another, then we should be able to proceed into the more steps of match and merge. So another issue that we have now is the variables situation, particularly in match. And that's basically, well, sometimes the values of the features or the features themselves are actually variables, and they need to be replaced by values when they're matching. So 2 structures matched, and suddenly the variables will have to be replaced by the new values from the structure that's matched with. And there, without decomposing this structure, we don't really know how you can replace the values without really digging into the structure and replacing them all individually. It has to be a holistic way of saying, aha, old structure, new values, join them together, and now suddenly the variables have been replaced by values. But of course, this is just to show again what this means in practice. So for instance, you have a completely empty binding list to start with. Then 2 structures have matched. And then from these two structures that have matched, you create a binding list. So Lex class X and then Sem class Y, for example. So how we create this binding list is a bit of a problem for now. But we know that similar transformations have been done already before by Neumann again. And we're trying to see how basically we can learn it. That's what we're working on at the moment. Okay, so that's basically brings us to the end of the experimentation phase. And now what we can do so far as a brief overview is that we can represent feature sets and even feature structures. More recent work, we've done feature structures as well. We can also retrieve values of features from structures of various lengths, as we saw on the graph. We also understand their scaling properties. We know how they behave. So this is based on work of Tony Plate, who wrote the thesis on this. And he had a formula outlined, which actually corresponds to our results of how they behave. And then we can also see that it scales quite well for HRR. And we know that we can run very small, very trivial examples of grammar processing, which means basically we can look at it more as a process than just individual operations, of matching or etc. And we know that eventually from the final merged structure, we can also get the values back, which is obviously very good news because we should be able to do that. So yeah, that brings us to the end of the talk, and there's just some references if anyone's interested. Any questions?
Thanks, that was super interesting. But I have lots of questions, maybe we can talk later.
Yeah.
Okay. But one of them is that you actually have two operations, right? So you presented the convolution part, but what you do is you do the convolution, but then you also use addition.
Yeah, but this is just a simple vector addition, so it's...
Yeah, but my question is, so what is the motivation to use addition? Because for instance, well, I come from computational linguistics, and I don't know if you're familiar with so-called distributional semantics. So, well, basically, it's just a vectorial representation for words, and they have, it's a lexical representation, but they have been moving, we have been moving recently to compositional distributional semantics, where you have, for instance, the meaning of mouse and the meaning of large, you combine them, you get the meaning of large mouse. Okay, so it's similar to what you're doing, but on lexical terms. And there are several methods that have been tried, and addition turns out to do this composition. So to get the meaning of large mouse from the meaning of large and mouse. Yeah. Many different methods. And addition turns out to be a surprisingly robust method. It's like it outperforms many more complex methods. Okay. But that's something that has been experimentally found. So what I found it a bit surprising that you just used it without because you could use multiplication, you could use there's other methods you could use. So I wonder if you have
because HRR is based on these two operations. So one is binding convolution, and then when you need to join vectors together, which it comes from the need to join pairs, no? You see what I mean? So green mouse, so feature value, feature value, feature value, because each construction has many of these feature value pairs. So you need a way to join these pairs together, and that's when we use vector addition. And it's kind of what comes with the approach. It's pretty much how HRR works. Convolution, addition, convolution. Maybe under some different approach, yeah, you're right, there will be other operations as well. Even within this family of vector symbolic architectures, there are many different ways to do these things, not just a HRR way, not just convolution way. It could be a binary way, for example. There's a binary Sparta code and things like that, which are completely different. So it's an XOR operation, for example, to bind these things, but not convolution. So it depends really which approach you choose and what you go with, and then you can see what you have available.
Okay, thanks.
So.
Other questions? So I have two questions, maybe because I'm not very familiar with the details, but so one is, since you want to learn a structural model, when I think of neural networks, my first guess would be that I would go for a recurrent neural network representation, but that's not what you did.
No, for now, you have to forget neural networks for a minute, It's kind of, it's a level up from neural networks. It's the numeric stuff that you can then implement in neural networks. So don't think of it as you go from symbolic to recurrent or something like this. It's what you do in the middle. It's the operations that are like a virtual machine in a way. So it's the stuff you do there, and then you implement it however you like. Okay, neural network, sure, recurrent, okay. If it even holds up, actually, because we tried before with this kind of stuff, and you know what the result. So yeah, so it's an interface layer that we're working on now. Then if we take it into Nengo, or if we take it to deeper level, then yes, okay, we will look at neural networks in more detail. But for now, it's kind of slightly higher.
So the validation you did, I didn't quite understand what kind of data was involved.
Well, just randomly generated sets of features. So you randomly generate anything, it doesn't actually matter what your features are or what your values are. What matters is whether you can get them back from the final structure.
Right, but the degree to which your operations are going to be appropriate depends on the regularities and kind of things that occur with real sentences and real structures.
Well, yes and no, because you have to think it's the operations that matter actually. So whatever the data is, it doesn't matter so much. It's what matters is how good convolution is at preserving information.
So the first step is to make sure the operations are reliably implemented.
Yeah. So to make sure that it actually even works, because people say, oh yes, from convolution you can combine things and get. Well, we don't know, right? So it's about testing in the framework of FCG.
And then in the next step, you would find out whether these operations are actually useful for your problem. So
well,
you first need to make sure that they work.
First, we need to make sure that they work, but already, we can use an FCG grammar, for example, to test it out. But this is it's a huge scale thing that we're doing now. It's more of a scaling issue than anything. So to test the limits of this system, and to see, okay, they work at 5 pairs. Fine, but we need more, for example, for FCG. We need to say, 50 or something. And then we test, does it actually work? Okay, dimensions go up, but it works, or something like this, It's,
No, just a short comment to extend the answer of the question on the addition operation. That actually, it's also very useful in this case because of the way the vectors are generated, because she explained the matching operation as a way to understand which original symbol, which was the vector of the original symbol that then you combined with others. And if you consider a set of feature value pairs, as she said, so a set of circular convoluted vectors that are then added up, and you try to retrieve one of the values of the circular convolution, actually everything else that you have added, it's just noise, so it doesn't disturb. So that's why actually the addition operation is very useful, because it doesn't matter how big the sets are if they are all added in the same level, because you can always retrieve.
Yeah, because in your cleanup memory, you store everything, so anything that's not there is just you don't know it.
It's basically noise in terms of the matching operation, and so just.
I actually had another question. So I wanted to pick your brain on something that also is a problem for us. So the difference between variable binding and similarity, like matching, and because, for instance, in distributional semantics, I assume you have the same problem. The representation for cat will be very, very similar to the representation for dog, just because, I will explain it in my presentation. Why? Okay. But then, of course, cat will not refer to the same thing as dog, so they cannot really bind the same variables in say, in a discourse. Okay. So there is a problem with using similarity for variable binding because things that are very similar do not need to bind. Do you see what I mean?
But yeah, it's true. We also found out that it responds more, it's more sensitive to this kind of content differences than it is to just being a longer structure or differences in how many pairs you have. So say you're comparing two structures, one has completely different values from the other one, but you know, so the same number of pairs and everything, but the values are different, and that will be completely dissimilar pretty much, even though the features are the same, but the values are different, and it's more sensitive to that than if you added, say, 10 pairs to the second structure, originally identical. That would be less of a drop in similarity than it is. So it's quite sensitive to content, but we don't know yet whether it's actually a good thing for us. It may be a good thing, the way the FCG kind of works. So, but again, you know, it's a matter of perhaps learning these things. We see it as the only way for, you know, to proceed. So, yeah.
So if I got it right, you still don't have a specific vector representation for specific words like dog, whatever. You don't have it now, right?
No, but a dog is just a vector. That's the representation.
Yeah, but do you have a vector, like a specific instance of that vector for dog, or you don't have it now?
I'm not sure I understand what you mean, because it's randomly generated, so it doesn't matter. Like anything for dog is just whatever. It's 5, 6, 0, 3, whatever. Cat is.
You
the
will
same.
always generate it randomly.
Yeah. So it's everything starts with a completely random population. You know, it doesn't matter what it is. So a dog can be represented as a feature value, a set, but essentially it's just a vector. That's your dog.
Okay.
So, yeah.
We don't have time for more questions, so...
Okay, yeah, if anybody wants to talk afterwards, it's cool, come and chat.
Let's
Yeah.
move on to the next.
Okay.
talk, and thank you.
Okay.